Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, we're going to summarize some of the top stories in science. Today on Exploration, we're going to continue our discussion about the whole question of the origin of the universe. We realize that Christian fundamentalists have not only targeted the theory of evolution, but they've also targeted the theory of the Big Bang as well, and they would like to ban both theories from high school textbooks. But today we're also going to talk about something different concerning the Big Bang, and that is the role of women in science. We realize that the president of Harvard University created quite a firestorm when he mentioned that perhaps there's some reason why women don't do that well in the hard sciences. Well, women are present in the hard sciences, especially astronomy. However, in the area of astronomy, it's rather scandalous that some of the biggest discoveries in the area of astronomy were done by women, and they never got the credit for it. And that must be very intimidating for a young female wanting to go into astronomy, realizing that some of the biggest discoveries in that field were made by women who never got the credit for it. And perhaps the most egregious example is that of Henrietta Leavitt. We all know that the stars are very far away, but precisely how far are they? In order to judge the distance to a star, you need what is called a standard candle. That is, a star that is the same throughout the universe. Therefore, a star that is very far away could be very dim or very bright, depending upon how intense its light is. So you need a standard candle, a star that doesn't change in brightness throughout the universe. And that's what Henrietta Leavitt found. She found that the Cepheid variables are, in fact, the standard candles anywhere in the universe, and you can calibrate them. You know exactly how bright they are using a formula that she came up with. However, she never got credit for it. So today, we can measure the scale of the universe using the result of Henrietta Leavitt, who in her own lifetime, and many lifetimes afterwards, never got any credit for her great discovery. We also have the sad story of Jocelyn Bell, a woman graduate student who discovered the pulsar, but it was her thesis advisor who won the Nobel Prize in Physics for the discovery of the pulsar. And we also have the sad story of Vera Rubin. Back in the 1960s, she was one of the first people to point to the fact that the universe seems to be full of something called dark matter, but her result was ignored, and only recently has the theory of dark matter been given experimental verification because of all the males who have now jumped into the field. So our special guest today is George Johnson. He's a writer for the New York Times Science section, also author of many books, including Fire in the Mind, Strange Beauty, and his latest book is called Miss Leavitt's Stars, the untold story of the woman who discovered how to measure the universe. And it's one of the scandals of science that Henrietta Leavitt never got the credit for measuring the universe. And then in the second half of Exploration, I'm going to bring on Michael Lemonick. It's a pre-recorded interview. He is a science writer for Time magazine, and he's going to talk about the latest results from the WMAP satellite, which give us a fine-tuning of the distances to the stars and, in fact, the age of the universe itself. So once again, our first special guest today is George Johnson, author of the new book, Miss Leavitt's Stars, the untold story of the woman who discovered how to measure the universe. The first question for you is, how did you first get interested in science as a youth?
I think it must have been a combination of the All About books, these great children's books about different scientific subjects, and then there was the whole space program, which was just getting off to a start, and I would see these wonderful pictures in Life magazine and the Saturday Evening Post, and sometime around the second grade, I wrote my first book, which was called The Solar System.
Oh, really?
It was made of, from Big Chief tablet paper and my father's shirt cardboards and crayons, with one page for each planet. But not a very penetrating treatment, I don't think. Nothing like David Sobel's new book.
Now, you also mentioned that you read science fiction as a child.
Yes, later on I did junior high school. I really got interested in reading Isaac Asimov and Ray Bradbury and Robert Heinlein, and that was very inspiring. I mean, there's this one Heinlein story that I mentioned in my introduction about the telepathic twins that can.
Yeah, I read that book too as a kid.
Oh, did you?
Yeah.
Oh, well, that just really the thing that really moved me, and that was the idea of them landing on this planet in a distant star system and looking back and seeing the Earth as a tiny little star that's part of a suddenly unfamiliar sky. It's all distorted by this different point of view.
Mm-hmm. Yeah, when I read that science fiction story as a kid, I said that, gee, two twins communicating telepathically faster than the speed of light? No, give me a break.
You were way ahead of me. I bought that hook, line, and sinker. Well, I didn't know it was fiction.
Now, why did you decide to write a book about Henrietta Leavitt, who, for the most part, is this tiny little footnote in most astronomy books, but most astronomy books wouldn't be written without her work?
Yeah, partly out of a sense of frustration, because I keep seeing these little footnotes or these kind of two-sentence glancing mentions of her work, and I started to get this picture in my mind of this woman around the turn of the century, kind of little post-Victorian times, sitting up in some dark room in the Harvard Observatory in Cambridge and poring over these star charts. And that image kind of fixed itself in my mind, and I thought I would start a book about measuring the universe with Henrietta Leavitt, just kind of to get into the book. But then I just really became very curious about who this person was and what, if anything, we knew about her, and was lucky enough to find some documents with a good researcher in the Harvard archives that helped flesh out her story a little.
Okay, well, let's now set the stage for exactly why her discoveries are so important. In ancient times, of course, ancient peoples would look up at the night sky, look at the stars, and wonder, how far are they? You can't throw rocks to hit the stars. You can't jump. Even the highest mountaintop, you can't reach the stars. So how did astronomers first begin to estimate the distance to the stars?
Yes, and they were able to estimate distances to things on Earth using triangulation. And we do the same thing with modern surveying, where you look at something from two different vantage points and see that it shifts slightly against the more distant backdrop, and you can use trigonometry to figure out how far it is. And Hipparchus, in ancient Greek times, did that with the moon and got a pretty good estimate of the distance. But the stars are so far away, even the closest star, that you could measure from two different parts of the Earth, and you wouldn't see any shift of the position, so you can't triangulate. So it was a big problem with the stars tiny and close by or enormous and very distant.
Now, this process is called parallax, and it's also the reason why we have two eyeballs.
Yeah.
So explain to us why we have two eyes rather than one eye, and if you injure one eye, it's quite difficult to judge distances.
Yes. If you think about your eyes as forming the ends of the base of a triangle, you're essentially triangulating unconsciously on things as you look outside. Like right now I'm looking out my office window at this old church across the street, and as I walk around through the window, the church, seems to move against the backdrop, and my brain is presumably doing some unconscious computations and giving me a sense of how far away that is. So if we were born with one eye, we would always be running into things because we didn't know how far away they were.
And that's also how 3D glasses work, right? Your left eye sees red, your right eye, the other eye sees blue,
right.
And your brain puts the red and the blue together to create a three-dimensional image.
Yes, right, or those old stereopticons where you have the two postcard images that are slightly different, one for each eye, and it gives you a 3D effect.
Mm-hmm. Okay, so the radius of the Earth's orbit around the Sun is about 93 million miles or so.
Right.
And so if you take a picture of the night sky in summertime and a picture of the night sky in wintertime, you've actually moved the telescope over almost 200 million miles, right?
Yeah. So you can imagine it's like having an eye on each side of the solar system, and from seeing how some of the stars, the very closest ones, shift a little between every 6 months. That was that gave astronomers a way to triangulate the distance to the very, very nearest stars, those just a few light years away. But most of the stars by far are so distant that you don't see any parallactic shift at all from season to season.
Now, children often say, gee, Daddy, how come the moon is following me? Everywhere I move, the moon is following me. But that's because the moon is so far away it has no parallax, and it gives you the optical illusion that it's always above your shoulder, right?
Ah, yeah, I'd never actually thought about why that was, but sure, of course.
Now, also, the light beam from the Earth to the Sun takes about 8 minutes, so the diameter of the Earth's orbit is about 16 minutes by light. But you just mentioned that the nearby stars are tens of light years away that are familiar to us every night. And so the parallax must be very small to the faraway stars, right?
Yes, it was just a fraction of a second of a minute of a degree. So it was a very, very delicate measurement and something that wasn't really possible until I think it was the 19th century when they really had equipment good enough to make measurements that finely.
Now, usually when we judge distances, we use what is called a standard candle. If I have a candle that is the same everywhere in a room, and I move the candle anywhere in the room, I can judge distances because the fainter the candle, the farther it is away.
Right.
It's the same candle. But stars are not standard candles, right?
Yeah, we had no way of knowing how bright they were inherently. So, again, it's the question of, is it very bright and really close to us? I mean, very bright and really distant, or is it very dim and really close to us, or somewhere in between? But yeah, without actually going out there in a spaceship and measuring it up close, it was a big mystery of how we'd know how bright they were so we could calculate their distance.
Okay, now let's go to the 1920s, where when astronomers had a pretty firm idea that the Milky Way galaxy, which we see every night, this swath of light cutting across the night sky, that the Milky Way galaxy was in some sense the entire universe. Could you explain to us how we viewed the universe in the 1920s?
Yes, that was one of the things that I really found most astonishing and that drew me into wanting to write a book about measuring the universe, was to realize that as recently as 1920, it was a matter of scholarly scientific debate whether the Milky Way was the whole universe or not. And if that were true, then something like Andromeda, which we now know to be a neighboring galaxy, would be instead just a very small little smudge, a little bit of stellar dust or something very, very close into Earth. And that's certainly what Harlow Shapley, one of the great astronomers of the 20th century, thought.
And in fact, wasn't there a great debate that you mentioned in your book concerning the structure of the universe and how far the stars really are? Yes,
in Washington, D.C. at the National Academy of Sciences. And Shapley took the position that the Milky Way is the whole universe and that there aren't any other galaxies. And Heber Curtis, another astronomer, took the opposing view that actually the Milky Way was just one of many, many of what Immanuel Kant had called island universes, or that there are many galaxies, and Andromeda was being one of them, and the Magellanic Clouds being a smaller satellite galaxy. So it was a very, very heated debate, and each man really left Washington convinced that he'd won.
So how big was the universe to Harold Shapley? In the early 1920s, he must have had an estimate as to how big the Milky Way galaxy was, and that was the universe. So how big was the universe to him?
Well, let's see. I can't really immediately recall the number from Shapley's calculations, but he used the standard candles that Henrietta Leavitt discovered to kind of measure out the Milky Way, and but it was just, obviously vastly smaller than the universe that we know about today.
Okay, well, now let's get into Henrietta Leavitt's work itself.
Yeah.
Tell us a little bit about where she was born, where she grew up, and how did you wind up as an astronomer at Radcliffe?
It was a very interesting trajectory. She was the daughter of a Congregationalist minister, very, very Puritan kind of upbringing in Lancaster, Pennsylvania. And at some point her family moved to Cambridge, Massachusetts, where her father had a church. And later out to the Midwest, to first Ohio and then to Wisconsin, Beloit, Wisconsin, and she followed the family there. And went to the family valued education, and they encouraged her to go to school, and she was in Beloit College in Wisconsin at first, and then later transferred to Radcliffe University back in Cambridge, Massachusetts, partly because she had relatives there. And during school, she had what was really just a general liberal arts education. She had some science classes, and, but mostly humanities. Toward the end of her time there, before she graduated, she took some astronomy classes that were taught by astronomers who just walked across the street from the Harvard University Observatory, and that's when she got hooked. And she took a volunteer position at the observatory right out of school, and this led into her job as what they called a computer, someone who was hired to do calculations.
Now, even today, grad students have to support themselves either by part-time jobs or scholarships or what have you. You mentioned in your book that she came from probably an upper-middle-class background, so she probably didn't have to worry about a job, right?
I think she probably... I was never able to confirm that, but it seems clear that she must have been of somewhat independent means, because there are these letters in which she talks about going off on cruises to Europe and things, and... she was being paid 25 cents an hour, which, if you put it into an inflation calculator, comes out to be about $5 in today's terms. So, basically what you'd make working at McDonald's.
Okay. So I understand that back then, of course, they didn't have calculators, and astronomers relied upon teams of women to do their calculation for them. Is that right?
Yeah, they tended to be women, and... it was considered a good job to get at the time. It paid better than working in the cotton mills, and of course, for someone like Henrietta Leavitt, it was a somewhat intellectual occupation. She seemed to enjoy it, and a computer at the Harvard observatories wasn't only adding up columns of numbers and doing calculations, but also studying these photographic plates of the sky that had been taken at the Harvard Observatory down in Peru. So it was pretty interesting work, I guess, for someone who was interested in astronomy, but then also very, very tedious, very, very painstaking work. And there was a certain sense that it was women's work, and the men would make the discoveries and talk about what the stars meant and interpret the data, but the women were there to gather it.
And precisely what did she do to change the course of astronomy?
The director of the observatory, Edward Pickering, he quickly realized that she was, very, very good at this, and even very overqualified. At one point, he gave her a raise to 30 cents an hour. And he assigned her a project of looking for variable stars in this haze of light called the Magellanic Clouds. This had been photographed by the Harvard Observatory in Peru, because you can only see the clouds in the southern hemisphere. They look somewhat like the Milky Way, except round. So Leavitt was looking at these plates and asked to look for stars that varied in brightness from week to week or month to month, and sometimes even from day to day. And she'd do this by comparing a plate taken, say, in January with one taken in February of the same part of the sky, and then would look for stars that had varied in brightness. So she was doing this, and she discovered just a very large number of variable stars within the Magellanic Clouds. So she was curious about how, what their periods of pulsation were, so she made a list, and at some point she noticed that there was a correlation, so that the dimmer a star was in the Magellanic Clouds, the dimmer a variable star was in the Magellanic Clouds, the more rapidly it blinked, and vice versa. And she drew a little graph and showed that there was a definite relationship between the star's rhythm of pulsation and its dimness or brightness.
And how could that be used to then establish a standard candle that could be used throughout the universe?
Well, essentially, since all these stars were in the Magellanic Cloud, she knew they were roughly the same distance from Earth. So it essentially meant that you could measure the rhythm of the pulsation, and from that you could derive the inherent brightness. It would sort of be like if an international commission had decreed that 50-watt light bulbs blink at a certain rhythm and that 100-watt light bulbs blink at a different rhythm, and that there was an exact relationship between the dimness and brightness. And then if you looked out your window out onto the town, you could tell by how fast the bulb was blinking how bright it was. And once you knew how bright it really was, you could calculate how far away it was using the inverse square law.
Okay, so what astronomers did was they looked at a variable star, calculated how fast it was blinking. That would then tell you how dim or bright it was. And since these are standard candles, that would tell you the distance to the star.
Exactly. And they very quickly found that there were variable stars within the Milky Way, and they were able to use this to get, kind of a sense of, they had to calibrate the scale, in other words, because they could say that, well, here's a variable star blinking, at this rate, so it must be so many, times further away than the second star that's blinking at another rate, but it was all relative distances at that point.
So she was aware, therefore, of the importance of her discovery, right?
Yes, it was clear, and that's one thing that has kind of been controversial. At least from some things you'd read, you'd almost think that she had just gathered the data and that Edward Pickering or someone had figured out the relationship. But if you really look closely at her paper, it's just obvious that she knew exactly what she'd found and why it was important.
So she published her results, so you could then infer from the publication exactly what she knew and what she didn't know, right?
Yes, right. And, there's always a question of, her being an assistant in a computer and working for Pickering. There's a question of how much input he had into the papers, but it was, right there with her name on it, and that's what counts.
Uh-huh. So in some reports I've seen, they sort of treat her as just a computer that just punches out the numbers, but she didn't know what the numbers meant. But you're saying that she actually did know that she had discovered a standard candle. Yeah, there's one part. Her papers are very, she was a very reserved, quiet woman, and her papers reflect that. And toward the end of one of them, she basically mentioned that this would, be a means of distance measurement. And she says it in such a way that, it just comes out very clearly, like, aha, you can see the light bulb going off in her head. So wasn't this heralded as a big discovery? Well, kind of, you'd think. Within astronomy, people quickly realized it was important, and an astronomer named Ejnar Hertzsprung used Henrietta Leavitt's stars to measure some distances within the Milky Way, and first started calibrating the yardstick. And then Harlow Shapley, who went on to become the head of Harvard Observatory, used Leavitt's standard candles to really map out the Milky Way and just show how great it was. But the real big breakthrough came when another astronomer, Edwin Hubble, found some of these Cepheid variables, they're called, Leavitt stars in the Andromeda Nebula. And once he knew that he had these standard candles there, he could measure how far Andromeda was and show that it was not, as Shapley believed, this little smudge close by, but that it was indeed a huge galaxy. Now, so what Edwin Hubble did was he took Henrietta Leavitt's result to show that the universe was a hell of a lot bigger than originally thought, right? Well, yeah, sure, because once you show that there's one galaxy, before long it was just one after another, and many of them were measured using Henrietta Leavitt's yardstick. And once they knew roughly how far Andromeda and some of the nearer galaxies were, they could use the whole galaxy as a standard candle. So if you made the not completely justified assumption that all galaxies are roughly the same size, you could see a galaxy that was smaller in
dimmer than Andromeda and rough out at least some sense of how far away it might be. And then more precise standard candles involving whole galaxies have been developed. But really, it's all the whole yardstick comes down at its very base to these Cepheid variables that Leavitt discovered.
So, in other words, during Harold Shapley's time, the universe was perhaps 50, 100,000 light years across.
Yeah, that's right.
And here comes Hubble saying the Andromeda galaxy is millions of light years across, and that the universe could be billions of light years across. I mean, this is a huge, huge discovery, right?
Yeah. No, I mean, it's really, as far as breakthroughs in the history of astronomy, going from thinking that the Milky Way was the whole universe, and I think the number it's coming back to me with 300,000 light years that Shapley had measured it across for the Milky Way, and and it was just a little bigger than that in his mind, the whole universe. And then Hubble finds that Andromeda is, according to his first measurement, 1 million light years from the Milky Way, and later with some revisions it turned out to be 2 million light years away, and that was just the beginning.
So, did people recognize the importance of Henrietta Leavitt's work, or was it simply a footnote even back then?
Yeah, totally a footnote. And, the people who got the glory were Hubble and his successors. And, people would mention Leavitt appreciatively, and but, basically, it was a footnote or a glancing mention. And some people have suggested that if her story had really gotten the airing it deserved, that maybe now we have a Leavitt space telescope as well as a Hubble space telescope. Or she did get a crater on the moon named after her.
Now, I understand she also passed away fairly early and wasn't alive really to see the enormous application of her discovery. Is that right?
Very, very sad. She It was clear from the correspondence that we found when she was exchanging letters with her boss, Edward Pickering, and she often was disappearing for 6 months, a year at a time, and having to go back to Beloit to stay with her parents. And there were allusions to some kind of illness, and it just wasn't clear what it was until toward the very end. She was hospitalized with stomach problems, and it turned out she had stomach cancer.
Well, that concludes the first part of Exploration. Our special guest has been George Johnson, author of the new book, Miss Leavitt's Stars, the untold story of the woman who discovered how to measure the universe. And if you want a copy of today's program, call the Pacifica Program Service at 1-800-735-0230. Stay tuned now for the second half of Exploration as we bring on Michael Lemonick. He's a science writer for Time magazine, talking to us about the very latest satellite data pouring in from outer space. And, of course, all that data is based on the work of Henrietta Leavitt. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. In the first half of Exploration, we had an interview with George Johnson. He's a science writer for the New York Times and the author of the new book called Miss Leavitt's Stars, the untold story of the woman who discovered how to measure the universe. And in the second half of Exploration, we're going to air a pre-recorded interview with Michael Lemonick. He's a science writer for Time magazine and author of the book Echo of the Big Bang. And we're going to explain how Henrietta Leavitt's work led to satellite data, satellite analyses that allow us to calculate the size of the universe, the age of the universe itself. All of it made possible because we now know how to locate standard candles throughout the universe, the discovery made by Henrietta Leavitt. So once again, our special guest in the second half of Exploration is Michael Lemonick, science reporter for Time magazine, author of the book The Echo of the Big Bang, and we will be discussing the WMAP satellite currently orbiting the planet Earth, giving us the latest cosmological data. First question for you is, why did you write a book about the creation of the universe and the echo of the Big Bang?
Well, I did it for two reasons. First of all, that topic is really the grandest topic you can imagine. It's the story of the birth and evolution of our universe, the biggest thing we know about. It's sort of where we all came from ultimately, and so that's just inherently fascinating to me, that extreme. The reason to write a book at this time was that I was aware that a number of scientists had put up a satellite in orbit that was looking at radiation left over from the Big Bang. It was going to look at this radiation in unprecedented detail, and that if the satellite worked, it would tell us all sorts of things about the early universe and about our cosmos as a whole that we didn't really know very precisely before. So it was going to nail down a lot of vague numbers and ideas. So that prospect excited me as well.
Okay, well, let me play devil's advocate. There are some people out there who say, harumph. I mean, the Big Bang, they don't believe it. It's so fantastic. The whole universe coming out of an object smaller than an atom. There's always some people who say that it couldn't have been this way. So what are your thoughts? What do you say to somebody who says they don't believe in the Big Bang theory?
I say that serious astronomers didn't really like it very much either back in the 1950s. They didn't take it very seriously because it was so preposterous. And gradually, over the next couple of decades, evidence began to come in that surprisingly confirmed this wacky theory. And as more and more evidence has accumulated, alternative theories that maybe you could still maintain had a possibility of being true have fallen by the wayside. There are a number of lines of evidence that tell us the Big Bang actually did happen, and they're pretty hard to refute.
Okay, well, let's get into them, starting with the redshift and the expansion of the universe. Explain how that works.
Okay, well, that's pretty straightforward. Back in the 1920s, Edwin Hubble, the great observational astronomer, measured the distances, approximate distances, to a number of galaxies beyond the Milky Way. And he was also using the redshift, that is the reddening of light that takes place when an object is moving away from us, to measure their speed of recession. All the galaxies you could see were rushing away from us, and the farther away a galaxy was, the faster it seemed to be moving. And the simplest explanation for that group of effects was that the entire universe as a unit was expanding, growing at a certain percentage rate every year. And if that were the case, then all distances would increase by that same percentage each year. And if that were true, then something that's farther away would move away by a bigger amount. Thus, it'd be moving faster in that same amount of time. So the short answer is that the expanding universe, which is really very firmly established, shows that the universe is getting bigger all the time. And if you run the movie in your imagination backwards, it was smaller and smaller and smaller in the distant past. So, and there's nothing that we can think of that would keep it from becoming arbitrarily small. So, if it started out very, very, very small and has been expanding ever since, that is the first evidence for the Big Bang.
Okay, and like you said, if you have a movie of an explosion and you know the rate at which things are expanding and you run the movie backwards, this means that you can actually calculate when the explosion itself first began.
Right.
So tell us a little bit about how cosmologists are so certain that they can calculate the age of the universe, even though no one was there to witness this event.
Well, I like to liken it to a high school geometry or algebra, word problem. You know, if two cars leave Pittsburgh and 10 hours later, going in opposite directions, 10 hours later, one car is 500 miles west and the other car is 500 miles east, how fast were they going and when did they leave? And you can calculate based on what you know about them today, their speed and their location, how long it was that they started on their journey. And I'd rather not do the algebra because I hated those problems in high school, but professional astrophysicists do those calculations all the time. So that's the basic way they calculate the age of the universe. That's the simple way.
Okay, so we talked about the redshift and the expansion of the universe, and there's something else called nucleosynthesis. That is the ability to predict the ratio of all the different 100 or so elements in the universe. So could you tell us a little bit about how the Big Bang affects the abundance of elements in the universe?
Yes, that's another key piece of evidence for the Big Bang. It turns out that in the very hot, dense conditions of the early universe, the original material of the universe, the simplest atoms are hydrogen atoms. That was the first thing that was created out of the Big Bang, first thing that's condensed out of energy, released in the Big Bang. And in the nuclear furnace that was the early universe, those hydrogen atoms, some of them were forged into helium atoms, and some of those helium atoms were forged into lithium. And if you assume the conditions that you can sort of predict in the past for the Big Bang, you can calculate at what rate those reactions should have taken place and how much hydrogen should have been changed into those heavier elements. And when you look around you in the modern universe, you look at interstellar gas and stars and so on, it turns out that the ratios are consistent with there having been that early hot condition. And we don't know of any other process that could have set the ratios of these basic elements throughout the universe at exactly this number. So that also says the universe was once hot and dense, and it's not anymore.
So when we look at our own sun right outside the door, and we realize that it's roughly 75% hydrogen and 25% helium, in some sense, I guess we can thank the Big Bang for that.
Absolutely. In a very literal sense. And anything heavier than lithium, or I guess beryllium maybe, was also created in some small amount. Any element heavier than that, up to iron, is then created inside stars. So we can thank the Big Bang for the sun, but we can thank stars like the sun, who long ago made the heavier elements and then exploded and seeded interstellar space with elements like carbon and so on. We can thank those for the Earth and for us.
And I guess for elements beyond iron, we can thank supernovas, that is the death, the explosive cataclysmic death of stars themselves that create the elements even beyond iron.
Exactly.
Well, now let's talk about the heart of your book. The heart of your book talks about something called the 3-degree microwave background radiation, which really turned the tide on the question of the Big Bang, and it's really given so much fertile grounds for experimental research. So explain to us, what is this echo of the Big Bang?
Okay, well, this is the third piece of powerful evidence, and in some ways the most powerful evidence that the Big Bang happened. I talked about the fact that the early universe was hot and dense, and about how such an early hot universe would create basic elements. But the other thing is that something that hot would have been shining, it would have been glowing brilliantly with light. And that light would have emerged and shone throughout the universe in all directions, from every point to every point. But as the universe has expanded since the beginning, the wavelength of that light has been stretched, and or you can also think of it as the hot universe cooling down to the point where the average temperature of space, interstellar space, should be about 3 degrees above absolute zero, 2.7 degrees. If you think of the universe as an object glowing at that cold but not zero temperature, it should be glowing with not visible light but microwave. And back in the late 1940s, several physicists said, look, these microwaves should be out there. This is the temperature that they should represent. And if you go looking for them, you should see them. You should see the afterglow or the echo of the Big Bang. The response from most astronomers and physicists was to ignore them. That was because, as I said, it was a pretty wacky theory. There were so many crazy things about it that it just didn't seem worthwhile to go and do this. About 18 years later, in 1965, 2 scientists from Bell Labs, who were looking for entirely different things, stumbled on this radiation. They didn't know what it was. They observed it, and they didn't know what it was. They said, it seems to be something coming from space. At the same time, about 30 miles away from their New Jersey lab at Princeton, a group of physicists had sort of rediscovered the idea of this background radiation. They were about 2 or 3 months away from finishing their antenna and aiming it at the sky when they got word that the Bell Labs guys scooped them. And as a result, Arno Penzias and Robert Wilson at Bell Labs received the Nobel Prize, and the folks at Princeton received a handshake. But the reason that the two got the Nobel Prize is that that they had fulfilled a prediction of this Big Bang Theory, and by fulfilling a prediction, they had put it on a very solid footing where it had been very vague before. So with that discovery and with its confirmation by the Princeton guys a few months later, the Big Bang went from being a wacky outsider theory to the leading theory of cosmology.
By the way, this is an aside, but do you think that the Nobel Prize Committee was fair in the sense that the people in the 1940s predicted this background radiation but were ignored? The people later who rediscovered it at Princeton, theoretically speaking, were looking for it and didn't have the equipment, but the people who actually got the Nobel Prize didn't know what the hell they were looking at.
Yeah, that's a very tough problem, and there's some very bad feelings all the way around, or most of the way around in this. I think that the Nobel Committee actually did the only thing it could do for the following reason. First of all, the folks at Princeton, although they don't like me to say it because I live in Princeton, really didn't deserve the prize. And the reason is that they had failed to acknowledge the earlier work of Alpher and Herman in the 40s in coming up with this prediction first. So the Princeton guys were not the first ones to make the prediction. So they shouldn't get the prize for making the prediction. They weren't the first to discover the stuff, so they shouldn't get the prize for discovering it. And where you might argue that Alpher and Herman, who were still alive at the time, should have shared the prize with Wilson and Penzias, the Nobel Committee the rules say you can't give out 4 prizes. 3 is the maximum. So they would either have had to pick one of the two, Alpher or Herman, or they could take the sort of coward's way out and pick neither of them.
Okay. Now let's talk about satellites, because satellites have really revolutionized cosmology and have placed it on a footing where it can be considered an experimental science. So tell us a little bit about the COBE satellite and, of course, the WMAP satellite, which is the subject of your book.
Okay. Well, soon after the discovery of this radiation, theorists realized that it should actually have a pattern to it. There should be a pattern of hot and cold spots in this radiation. The reason is that the modern universe is actually very lumpy. We have very large structures, superclusters of galaxies, which are concentrations of matter, and in between them, there are big empty spaces where there's essentially nothing. And for that structure to exist today, it had to be present at least in rudimentary form from the beginning, so that gravity would have worked on areas of slightly higher density, making them more and more dense, and emptying areas of lower density. So there had to be some kind of pattern in the matter early on, and that pattern should have been reflected in hot and cold spots in the radiation coming from that matter. So let's go look for these patterns, and by looking at them, we may be able to say very many useful things about what conditions were like in detail back then. So they started looking from the ground at first, and they couldn't see them. These hot and cold spots were much too faint to see from the ground. They started launching balloons, but again, you couldn't see them from balloons in the early 70s. So in the mid-70s, a number of cosmologists got together with NASA to start building a satellite to get up above the contamination of light and atmosphere from the Earth and to look for these hot and cold spots. And finally, remember, they started in the mid-70s. In 1992, at last, they detected this radiation. They detected the hot and cold spots. The Cosmic Background Explorer, or COBE satellite, detected these things for the first time, which was a great confirmation for Big Bang Theory. Unfortunately, what they hadn't realized when the satellite was designed was that if you don't look at spots of the right size, you're not actually going to learn anything useful. And the spots of the right size were smaller than what COBE was able to see. So COBE confirmed the existence of hot and cold spots, but the ones it found were too big to say anything useful. So immediately, scientists started thinking about making another satellite that could see the much finer-grained hot and cold spots that would tell them what was going on.
Okay, and when the COBE result came out, the authors of the report published a picture, a photograph, showing a very kind of out-of-focus picture showing some of the dark and bright spots. And George Smoot, one of the leaders of the group, called it the face of God.
Yeah, I was there at the press conference when he said this. He said, if you're religious, it's like seeing God. And he was actually trying to make an analogy. He was trying to give you a sense of how important this was. But the press just picked up on this comment and went wild with it. And he got a huge amount of attention. He also got a book contract with, the report is $2 million. He got an enormous amount of publicity, and many people thought it went to his head. And he kind of started thinking about this as a project that he himself had carried out alone, when in fact it was a large team, and a lot of people got annoyed with it. So when they got together to make this next satellite, many people really didn't want George Smoot on their team, and he was kind of frozen out from several of the team.
Okay, well, it's not really the face of God, but it is a baby picture of the early universe when it was about 300,000 years old. So explain how we know that this is a baby picture of the universe when it was quite young, 300,000 years old.
Well, we basically know that the light generated from the very hot matter in the Big Bang at first couldn't travel very far because atoms were split into positive and negative charged particles, and light would just get absorbed if it tried to travel any distance. So the light was shining brilliantly, but it couldn't travel any distance. But finally, at a certain point, it cooled to the point where atoms could actually form, light could travel freely, and that light began streaming through the universe, and has been streaming ever since. And we can calculate what the density and heat required for that event would be. We can calculate about how long after the Big Bang light would be able to travel freely. And so any light that we see coming from the Big Bang had to come from that first moment when light was able to shine freely. Once it shone freely, it never stopped until we caught it in our telescopes.
Okay, now let's talk about the WMAP satellite that everyone's talking about. Specifically, what were its characteristics and what were some of its rather stunning conclusions that made the front page in many newspapers around the world?
Well, its characteristics were basically that it was a very carefully built set of microwave detectors operating at 5 different wavelengths, and that the technology itself was not particularly innovative. It was pretty much off-the-shelf technology. Of course, it was off-the-shelf mid-90s technology compared to the COBE technology of the mid-70s, so it was much more powerful. But what distinguished this from other satellite projects is that the builders were extraordinarily careful to eliminate any possible sources of error. That is to say, the satellite itself, if it got too warm, could send out its own microwaves and confuse the signal. It could electrical currents going through the electronics could send out their own microwave signal, which would confuse the answer. So they, first of all, designed it to have an absolute minimum of these external errors that could confuse what they were seeing. And secondly, they went to extreme lengths to understand and characterize what errors they would introduce. It's unavoidable to have some kind of contamination from the satellite. So I mentioned that if part of the satellite heats up, it can cause a false signal. They worked to keep it from heating up by putting on shielding and so on, but they also put dozens and dozens of thermometers at strategic points along the satellite. So if it did heat up, they would know it, and they would say, exactly this much heat caused this much contamination, we can account for that. And it was that extreme care that characterized this satellite. The other thing that was important is that, unlike most NASA satellites, this one was built by the scientists themselves, not by contract engineers. And most of the instruments were actually put together on the campus of Princeton University in a clean room that they designed for the purpose, not at the big NASA facility. And the reason is that the closer the scientists are to handling the actual experiment, the more they can control for the factors they need to control.
Okay, now let's get into some of the rather astounding conclusions coming from the WMAP satellite. The first one being that the universe is 13.7 billion years old, plus or minus 1%. How did they calculate that number, and are they really certain that the universe is 13.7 billion years old?
Well, the answer to the second question is that they are quite certain, and the best measure of that is that no one, to my knowledge, astronomers are friendly with each other, but they're also competitive. And so the minute these results came out, everyone scrutinized their results, scrutinized their techniques of analysis, because it would be deliciously fun to say, oh, guys, you forgot to carry the 3, in the third column, and your number is off. And we've proven that, we've got the right number, you had the wrong one. Would have been very embarrassing for the math folks. To my knowledge, nobody has challenged this conclusion, which is a good sign that they really are sure and they have a right to be. The way they calculated it is they actually used a simulator, a computer-based simulator, to create artificial patterns of hot and cold spots in this early universe by varying a lot of different cosmic parameters. They would say, okay, well, say the universe is made of this amount of stuff, and say that this light began to shine freely at this particular time, and say the universe is this particular age, and look at the structure of the modern cosmos, where the galaxies are, and so on, and what would the pattern of hot and cold spots look like in that case? Okay, now let's vary one of these numbers by a little bit. What would it look like in this case? Now let's vary another number. And they went through and varied each of these numbers and many more dozens of different times, produced literally tens of thousands of simulations. And when the actual pattern was revealed by MAP, they went and did a statistical analysis of that pattern and of all of those tens of thousands of simulated patterns. And they found the one that most nearly matched the actual universe and looked at what the numbers were. And the numbers are the ones that they determined were, in fact, the real numbers. So they actually built model universes in their computer and went back and compared them with the real universe and picked the one that most resembled it.
Now, cosmology historically over the decades was sort of like the laughingstock of the scientific community because it kept claiming that the age of the universe was in some sense younger than its stars and younger than the Earth. Hubble himself computed the age of the universe to be about 1 billion years old, and yet we know that stars are billions of years old, and the Earth is probably 4.5 billion years old. So do you think finally that we've gotten many of these contradictions out of the way, and this number really fits so that no one else is going to say that that can't be the age of the universe because there's a star that's older than that? Right, and the answer is that as cosmology has... as instruments have improved and as our measurements have improved, as we can see farther and more clearly with such devices as the Hubble telescope, we can refine our understanding and make our numbers more precise. In fact, the reason Hubble got the age of the universe wrong is that he had estimated the distances to the galaxies incorrectly with his very crude methods. He basically looked at them and said, well, this one seems about twice as bright, so it's probably twice as far away, but that's very, very, very rough. And so he was using a wrong input in his calculation. That's one reason that nobody took the Big Bang very seriously. In fact, that according to Hubble, it said the universe was younger than the Earth. So let's forget this theory. As the techniques have become better, the numbers have become more believable, and so it's not surprising that we've gotten to a point now where we can say, no, this is the age, and it's not going to change anymore. And in fact, there's no strong argument that there are any stars older than 13.7 billion years. Okay, another shocking conclusion from the WMAP satellite is that matter that we see around us only makes up perhaps 4%, a trivial amount of the total matter energy content of the universe. So tell us a little bit about dark energy and dark matter. Okay, well, yes, that's as the astrophysicist John Bacall said at the press conference announcing these results, we now are forced to face
the fact that has been looming for a couple of decades, that we live in a preposterous universe in which the stuff we're made of and everything we know of, the stars, the planets, the galaxies, amounts to only 4% of what's actually out there. More than 20% is made of something called dark matter. We don't know what it is, but we know it exists because it exerts a gravitational influence on visible matter. In particular, galaxies, spiral galaxies like the Milky Way, for example, spin too fast. They spin so fast they should actually be flying apart. Long since have flown apart. But the fact that they're not suggests that there is some kind of matter whose gravity is holding them together. We can't see it, but there's a lot of it. And since we can't see it, we call it dark matter.
Well, I'm afraid that's it for Exploration. Once again, we had two special guests today. The first special guest was George Johnson, a science reporter for the New York Times and author of the new book, Miss Leavitt Stars, the untold story of the woman who discovered how to measure the universe. And in the second half of Exploration, we had a pre-recorded interview with Michael Lemonick, science reporter for Time magazine and author of the book Echo of the Big Bang. And the book is based on the WMAP satellite, which in turn relies upon Henrietta Leavitt's results to measure the universe.